So the final search algorithm that we're going to look at is something called a binary search. It's called a binary search because at some point during the algorithm you're going to be making a choice of one of two options, binary, on or off. The cool thing about a binary search is it's actually a recursive algorithm, and it recurses by dividing the list in half, very similar to the merge sort. And if you remember, the cost of the division in half for the merge sort was big O of log n. The additional cost for the merge sort was multiplying by n for the merge aspect of the merge sort. Binary search doesn't have to deal with anything like that. So its actual big O notation is big O of log n. That's what it is. So this is actually pretty powerful when you think about it. So if you think we have a value of n and the number of steps, if n is 1,000, for example, what we end up with, let's calculate this. If n is 1,000, what we end up with is about 10 comparisons to actually find the value that you're searching for. If n is 1,000,000, you end up with approximately, let me just scale this up, 19.9. So about 20 steps for 1,000,000. 20 steps, 20 comparisons, 20 operations in order to find an element in 1,000,000 elements. That's an incredibly powerful tool. So of course, binary search is commonly used in quite a few different pieces of software. What we're going to look at right now is how does it actually work. We did mention that it is a recursive algorithm. And it's a pretty straightforward recursive algorithm and fairly easy to implement, very short in code. The way that it works, as I mentioned before, is you divide the list in half. So if we look at this list and we have it numbered 0, 1, 2, 3, 4 in terms of its indices, we take the number of elements and we find the midpoint of those elements. And we know looking at this that the midpoint is going to be index 2, which is the value 4. We know it's the midpoint because there's the same number of elements on both sides. Now, of course, if you have an even number of elements, you have to decide whether you're going to round up or whether you're going to round down in order to achieve your effective results. So the way that this mechanism works is, think about it and go back about 10 or 15 years to the old school days of phones, and you were trying to search somebody up in a phone book. So let's say, for example, you were looking up John Smith in the phone book. Well, you know Smith starts with an S, and S is a little bit more than halfway through the alphabet. So you wouldn't start on page 1 of the phone book. That would take you forever. What you actually end up doing is you go to a little bit more than halfway of the phone book. You say, well, is the name I'm looking for on this page? No. Then if it's less than the values that are on that page, then that means that you need to go to the left in the phone book. However, if the number is greater, or if the name is greater than the names on the page, then that means you need to go to the right of that page. So it works the same way with a binary search. So let's say, for example, we're searching for the value 97. We're going to say, well, find the midpoint. And we know the midpoint is going to be index 2, which holds the value 4. And we say, well, does 97 equal 4? No. This is our base case. Our base case is when our number is equivalent to that midpoint, their midpoint value. So since it's not, now we need to make a decision. Do we go left or do we go right? So we say, well, is 97 less than the number 4? No, it's not. So we don't go left, so we must go right. So that means we can actually eliminate everything up to and including index 2, which holds the value 4. So that means the next step is to look at only the elements left over, which are 5 and 97. So we have to find the midpoint again. Now let's assume that we round down. So that means the midpoint of this would be the value 5. We say, okay, well, the midpoint of value 5, and we say, well, does 97 match the value 5? No, it doesn't. So again, we failed on that. So we have to check, well, we got to recurse, and we recurse by dividing the list in half. We divide the list in half by taking the midpoint and everything to the left. Well, there is nothing left, so we don't have to worry about that. But to the right is another value, 97. So the first thing we do is we find the midpoint. And the midpoint, of course, is going to be the only value there. And we say, well, does the number 97 match the value at the midpoint? Yes, it finally does. So that means that we're all done. We found the number, and so we return that number back to the programmer. So how many comparisons did it take? Well, let's see how many it takes us in the worst case scenario. We have 5 elements. So we have 5 elements. And we actually do this. What we end up with is a number of 2.3. And if you look at this is actually fairly accurate. We're pretty close to that. We did the initial comparison. We divided the list in half. We did another comparison. We divided the list in half. So we ended up with 3 steps. Now it could have been less if I had chosen to do to round up rather than round down. We would have been finished up here instead of down here. But that was a choice that I made intentionally to illustrate my point. So what we see here is now that we have 2 effective searching algorithms, both serve benefits and drawbacks in terms of the linear search can work on unsorted data, but the binary search is much faster as long as the data is sorted.